So the statement of the result in the embedding case if phi is an embedding into Cn, for example, so biholomorphic embedding onto a closed manifold, onto a closed submanifold, that was the situation we just considered. I sketched a proof for you, and I think you can fill in the details easily. Then, for every point P in X, there are what I would call perfect coordinates. And what that means is, in the picture, if you have X, and then you have Cn, and here's the first axis, say the Z1 axis, and here are the rest. Then you can choose your base point of the parameterization. You're given P, I didn't say, so perfect local coordinates. So the word here, local, is of course obvious. So you're given P and X. Then there is, and then I'll draw my picture again. And then please ask all the questions you want. Then there's a neighborhood, for example, of 0 in the Z1 plane, which you have thickened to be a product neighborhood in Cn. So this is a product neighborhood, so this is a disk of dimension 1 in the X, in the Z1 direction, product of a disk in dimension n minus 1. So the complementary normal direction of S is n minus 1. So you have this local picture here that is completely stupid local picture. And the disk, this is the mapping phi. Oh, well, this is the local version of phi. Let's call it phi has a local version of phi. We have maps 1 to n minus 1 into Cn, locally biholomorphically, so that in fact the piece on the Z1 axis, this is phi hat of the Z1 axis, delta, I call that delta 1, and these directions are the images of, well, I will color them yellow, of the remaining axis. So it is a local picture, it could not be better, of X. Could not be better. It gives it as a curve and locally, and it gives the normal directions here, the orthogonal directions if you wish, these are the image here. And so your local analysis can be done really here. So local analysis here. Now, should we discuss that or not? X is very mysterious itself. You're starting to ask a question, Nico. What are you going to ask?
Like, what do we gain out of that?
We gain, if you want to study local, you want to study holomorphic functions locally, all I'm saying is you only need, locally, taking into consideration that your manifold is a one-dimensional called the Z1 axis. You only need this picture here. You don't need any global picture at all. A priori, if your manifold is embedded, who told you how that's embedded? Some guy comes and says, well, it's embedded as a submanifold of Cn. So what? And you say, I want to do a local analysis on this manifold. And I say to you, well, okay, you can do it, because if it's embedded globally, it means locally we can do this with coordinates. Right? And that means really in a strong sense. In the strong sense that the coordinate patch that we really have is the Z1 axis here. And we even control the orthogonal directions locally in Cn. Probably you want to make a remark, is this the way you think about things? I hope.
Yeah. And I think of it as a normal bundle and kind of look at the tubular neighborhood kind of stuff, I guess.
Yes, but probably you're thinking globally even.
Yeah.
So it's not so clear that you can make this picture you can make this picture global. What Prof is saying here, he would like to make a tube around this, so this is sort of a global picture. We call this the tubular neighborhood theorem. And what happens is, and we talked about this in the pausa, of course, locally, you can make sure that these normal directions don't intersect when you go out. But globally, it's dangerous. So what happens, because there may be more and more curvature and maybe oil. So what happens is this tube must shrink as you go to infinity. See, you can do it locally at one point, and the tube must shrink. Okay. But that's almost starting to approach deep theory. Okay. So this is how you get local coordinates on a Riemann surface that's embedded in Cn. And now some comments. The first comment is the theorem of Hassler-Whitney, and I should say Whitney because he was an American, proved very early in the subject, but it proved very early in the subject of calculus on manifolds, not in the subject of complex analysis. He was one of the first truly American mathematicians, actually. He says M is a manifold, so this should be a smooth manifold. Maybe you assume para come back. I always worry about what's assumed topologically here, but it doesn't matter to me. And we assume this manifold is of dimension n. A manifold. And Whitney says this manifold is embedded, can be embedded as a closed submanifold here. Of course, this is a smooth embedding. In R2n plus 1.
I think paracompactness is not enough when you second countability.
It's very close to the same thing.
You need countably many components.
Of course you need countably many components for this, right? If you have uncountably many components, Prof got a good point. If you have uncountably many components, then you can't do this, right? So, okay, second countable. I know. So, any manifold can be a second countable. Okay, but I'm glad you mentioned it. So that means, from the point of view of smooth embedding, you have some highly complicated manifold, and it's in R2n plus 1, and this can be pushed down. And just pushing down, a lot of people really were interested in how far can you push this down. I'm not sure the best result, but it's something like maybe 3/4 of n. So it's 3/4 of, 4/3 of n, something like that. I don't know. Anyway, so this is your picture, and you have the same thing. It requires the inverse mapping theorem. Every point has a neighborhood, which is a thickened neighborhood, and can just be realized in R 2n plus 1 as a thickened neighborhood of something completely trivial, a disk or a ball or something like this, and thickened in this direction. And that's the way you should think of every manifold. Okay? And the proof I gave you, it's the inverse mapping theorem, always. We had a little bit of an argument with Nico on this in the past, but you now agree. It's just a question of making sure these normal directions don't move too much when you're in here. And that's the proof. Okay? So that's Whitney's theorem. It's not very useful in some sense because this embedding is abstract, and but maybe it's interesting. And then in the 1950s, Bremen proved the same theorem in complex analysis. Well, the analogous theorem. In complex analysis. I will not tell you the statement of his theorem because you have to understand a bit of higher dimensional complex analysis, but for Riemann surfaces, for X, a Riemann surface, well, let me be very precise with the condition. First, a non-compact Riemann surface so any horrible thing you can think of topologically, there is a closed, in fact, generically, I don't want to get into it, there's a closed biomorphic embedding. Of X into C3. Every non-compact Riemann surface is embeddable in C3. So that means you have here C3, so this is C3, highly nonlinear. You always have these coordinates I was talking about here, but they're homomorphic coordinates now in C3. Now you will find, perhaps this not very exciting, but is an open problem. Can we get X in C2? It's not known. And it's a little bit interesting because it's a question. So what you would have is this mapping phi in C2. And phi is given by two functions. On the Riemann surface. And it has to be locally bihomomorphic at every point. This has to be injective. And this map has to be a closed embedding, it has to go to infinity as you go to infinity here. So it's a question of creating two functions which have marvelous properties together. Okay? So when I was starting in this subject, I actually constructed a function where x is a unit disk, and it was very, very hard to do. You understand? I take the unit disk, can I embed it as a closed submanifold of C2? And in the meantime, there are many deep theorems not proved by me but other people where this is true of anything. So let me tell you, just in case you're curious, if x is what is called a finite Riemann surface. By the way, this already tells you have a huge number of holomorphic functions on this thing, because you've embedded it in C2 and you have all the functions just you get by restriction. Right? So this is a really interesting theory. So if x is a finite Riemann surface, so I don't know, this is the classical notation. I mean Riemann surface with boundary. With boundary. So x plus the boundary of x is compact. So you're pushing compactness, but it's not compact. So it looks like a pair of pants or something like that. So a pair of pants, maybe here would be the boundary pieces of the Riemann surface. And here's a finite Riemann surface with three boundary surfaces. This could be embedded in C2. So if you know something about infinity, in this case, you know that there are boundary curves like this, and you embed in C2. Okay, so that tells you every non-compact Riemann surface is a wonderful thing. It's sitting as a holomorphic curve in C2, in C3. So the lingo is non-compact Riemann surfaces are just holomorphic curves. In C3. Now that was the first way of realizing Riemann surfaces in C3. The next way is the second realization. As zero sets of functions. And maybe this is a better way. Maybe. So in other words, you might have several functions. So in other words, you might have x is the set of zeros of a number of functions. I don't know, some big number of functions, k functions, in some big Cn. Why not? Okay. So let's look at some examples. What about this function in C2? X equals let me write it down, two variables. This thing. I mean, that's maybe the first thing you would write down. The zero set of one function in C2. It should be one-dimensional, so it should be a Riemann surface. But then you learn to draw a picture of this. This is Z2 equals 0, and this is Z1 equals 0. And this thing has a manifold entered here, a Riemann surface entered here, and a Riemann surface in here. But the problem is, as you see, there's a singularity. So there's a singular point. Okay. And this example is a little bit unfair because this example is not irreducible. And the point is that irreducible means you can't do the following. Here you have one component which we call this one, this pink component. This is one irreducible component. And maybe you have another, and you have the other irreducible component here. The yellow component is also an irreducible component. And of course, these two things are manifolds, so it doesn't count. The singularity doesn't count because it's just the union of two manifolds, right? You're looking a little bit upset.
What does irreducible mean?
Okay. It means, I'm going to tell you, you won't like my words. It means not reducible. Which means you can't write it as the union of two open sub manifolds.
Okay.
See, this thing, open subset. See, this thing is somehow open here. Well, you can make all sorts of examples like that. And then you make the next example. These are examples of the first course anybody takes in the subject, but this is called topics and concepts. This is an interesting thing. This is a very interesting example. Watch this example. I'm even going to call this V, but it's going to be contained in C2 again. So it's going to be defined by one function again. Everybody loves this example. It's the first example. Okay? Now this, if you're at all interested in mathematics, you should really look at this example at the point 0, 0 in what you call P0, say, in V. Okay. Now the first thing you do as a child, my grandson, is you look at this thing because you have no experience in complex analysis. You look at this thing over R. Now why not? I mean, it's easier to think about over R, right? So what we've got here is the x-axis and the y-axis, and you have x squared equals y cubed. I may change the role of x and y in a minute. I don't know. So x squared equals y cubed. Maybe I want to try it the other way around. Just let me think a minute. Y squared equals, yes, maybe I'll do this the other way around. Y squared equals x cubed. I don't think. Okay. Yeah. You notice here that y squared is always a positive number. So x cubed has to be always a positive number. So that means x is always a positive number. So it means, I think if you look at it, x is always a positive number. And there will be two values of y for every value of x, obviously, because y squared is equal to x cubed. So it looks something like this. You may not like this picture, I don't know. There's something terrible happening here. There's something terrible happening at 0. Okay. This has, this in some sense is a parameter. Maybe I drew it wrong. It depends on your rule of x and y. But something terrible happens at 0. So I recommend you think about this. This has a name. Nile. Maybe I didn't spell Nile right. Parabola. So you can have singularities, and this is reducible. So this is reducible. So you make it. This is a non-trivial example. This is reducible. Irreducible. So there are all sorts of problems with singularities, and so you want to avoid singularity. Singularities. And now, so you have a great idea, because you learned something from Mickey Mouse mathematics. Your idea was this: if you're in Rn, yeah. I'd like to tell you about elementary mathematics at the same time. If you're in Rn, you have some function, f equals 0, and you want that to be a smooth manifold. And the way you understand for it to be a smooth manifold is that you have the gradient vector of f at 0. I call it the gradient for people who are in physics. Okay. The gradient is not canonically defined, but if you have a metric, which we do in Rn, then it's defined. Everybody knows the gradient, what the gradient vector is. I think it's a column vector. It's partial f with respect to x1. See partial f with respect to xn as a vector. Right? And you know that this gradient vector is orthogonal to the tangent plane, and that that's the way the function grows and moves, and the tangent plane moves in this way, and so on. It's the gradient vector is telling you all of this, right? And so that's very good. And in fact, then you say, well, let's look at some example. That's beautiful. This is a manifold. Everything. Let's look at some example. For example, f equals x squared plus y squared. That looks pretty good. So minus 1, let's say. So that's great. Let's see. The gradient vector is partial of f with respect to x, which is 2x. Partial of x with respect to y, which is 2y. So this is 2 times the vector xy. Right? And that's pretty interesting because we have the circle, which is the manifold f equals 0. And the gradient, if you're on the circle, if you're here at this point xy, the gradient vector is xy. It's confusing. If you're at the point xy, the gradient vector is xy. But you think of the gradient as being in the tangent space at the base point. So this gradient vector is a wonderful thing. It moves along the manifold and so on. So it's really good if you're in some classical setting. The gradient is telling you whether this thing is smooth or not. Right? It's one function. And that's the same thing. So same thing in complex geometry. Same thing in complex analysis. And so I will formulate it here, okay? And then if you're trying to understand something, you better formulate it in a good way. So the gradient of something is the metric, I don't know, metric version of df. You know that, right? It's the metric version of df. df is a one form. You know about one forms now, right? Everybody, right? In calculus and that. It's the metric version of df. Okay. So what's happening here? You have x someplace as the set of points p, for example, in Cn, such that f1 of p equals fn of p. A bunch of functions. I said k. P equals 0. And you've just seen for one function it can be horrible. I mean, at least I gave you two bad examples. But if you have many functions, you ask the question. So the question is, the obvious question is, when is this? When is x a Riemann circle? So, what is it a manifold? Okay. I hope you have heard this question before. If not, you're hearing it here for the first time, and please remember the answer. And remember how to deal with it. Well, you look at the holomorphic theory and the real theory are quite similar. So you look at the real theory. So the question of smooth structure. So in other words, M equals the set of points P in, say, some big Rn, such that F1 of P equals F K of P. Okay? Now there is a nice thing here. So the first thing to consider is here's an n, which is going to be x in a minute. Here's going to be m, and here's the level set of, you have a great idea here. You get a map f, which is defined by f1 through fk. And what your idea is that this is the map f, and it goes to rk, and your hope is that somehow this RK parameterizes the level set of f in a beautiful way. So here's f equals 0. That's the original level set. And somehow, if you're moving in this normal direction, you should hope that you get a beautifully parameterized thing. And I hope you know that's called the theorem on constant rank. Okay? Theorem on constant rank. If anybody, please know several theorems in mathematics, and that's one of them. The theorem on constant rank. Okay? So, what is the theorem on constant? What is it? How do you determine the rank of that? Rank of f at a point. Okay? So, physicists are here. Physicists believe, correctly in some cases, usually maybe not got quite correctly, but you have to study physics, which is nature, and you don't care whether you're quite correct or not, because you have to deal with it. And what you believe in physics is you can linearize a lot of stuff. You're constantly, if you look at what you're learning in physics, you look and in fact you're linearizing all the time. Yes. And that's the process that you have to do. The rank of that is this. This is the rank of at P of df, the differential at P. Right? So the infinitesimal guy, the first order development, is value, linear part, higher order terms. Linear part is this guy. Yes? If this linear part is going completely bananas, you're in big trouble. Okay? You're in big trouble. So, I remind you, recall the trouble. If you know about this trouble first, you might never do mathematics because it's too threatening. Every closed subset of something like, say, Rn, we're over here, Rn, is the level set, is such a level set. Namely, like I've written here, f equals 0. That should disturb you. Every closed subset, you can imagine what I'm talking about, every closed subset. That's a horrible thing. You understand what I'm talking about? Here's this terrible closed subset. It's just unbelievably bad. And here's the point P here, and here's f of P equals 0. And it's not a manifold at all. It's any arbitrary closed subset. Okay. So that's terrible. That has no tangent space, no nothing, no nothing. This is a remark of immutable red. Every closed subset is a terrible thing, right? I mean, so you need some conditions. So the physicists are right. You shouldn't be considering arbitrary functions. Arbitrary functions don't exist in nature. They are objects of mathematics that we complete mathematics to get all these functions so we can deal with it. But they don't exist in nature. You can't tell me that an arbitrary closed subset exists in nature. I don't believe it. So it's just a very convenient thing to work with, arbitrary closed subset. However, if rank of f is constant, in a neighborhood of P, then there exists perfect coordinates at P. Okay, that means same thing that I said before. Here is f equals 0. Yeah. Here are the normal directions. This whole picture takes place in Cn. This manifold. Ooh, what's the dimension of this manifold? I don't know. This manifold is, say, L dimensional. Oh, no, we know what this manifold's dimension is. Let's let R equal the rank of this constant rank map. So the dimension of the manifold is n minus R. Right? It's n minus R, right? Because, you see, the linearization moves transversally here. This is a generalized gradient, which you know to call Jacobian matrix, right? So then you have the perfect coordinates by the above discussion. Here is R, n minus R, and here is here is our R, and you're thickening this guy in the direction of the rank, in the gradient, and you have the manifold is the picture I just said. You have this mapping. Of course, this is not mapped. F can be realized here basically as this map, and then this thickened map looks like that. Well, yeah. The map on the, there's only one theorem here. It's the constant rank map. Theorem. Theorem on constant rank. Auf Deutsch sagt man Rangsatz. Yeah. Okay, and you can write down this thing in coordinates. So, and if you don't have this condition, you see any example that we would have just discussed here does not verify that condition. These functions defining these singular things, so, well, yeah, and for fun, actually, you can see what happens over the reals. You can see what happens over the reals here. The rank is, here's this mapping, the rank of this thing is xy, so the rank of f, in this case, is at the point xy, is 1 or 0, and it's 1 if xy is not equal to 0, and it's 0 if xy is 0. Well, then look what happens. The level sets, you see the level sets here, rank is good. Rank is good if you go outside. Rank, I said rank up good. So, and here locally, you see you have a beautiful local thing. Rank is good, rank is good, rank is good. And then we go inside, 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 and then inside, and it collapses completely. It collapses completely. Okay. So singularities happen when rank collapses. Okay. So the same theorem is true homomorphically. So this theorem, I like it much better out there than Einstein. Because it's just one word. And it's, I think in English, the only way I say is constant rank theorem. Look, yeah. But I like in German when I get this lecture in German, the Rangsatz. I like it. And this is Rangsatz. It is true over the, is true, holds in the homomorphic set. So, i.e., therefore, F equals F1 to Fk and Cn to Ck homomorphic. It's the same proof. K functions, you write the Jacobian, it's an n times k matrix or something like that. Yeah. It has to have constant rank, and that's it. Okay. So those are the two main things, and the key. The key. Key. I wrote my wife on Facebook last night, and I said something important. And I wrote 4 times this. So here I will write 5 times. Key is Rangsatz. So that is the key. And now we dealt with embedded Riemann surfaces in C3, and maybe if we're lucky in C2. We dealt with getting coordinates. We dealt with realizing these surfaces as, oh, I should tell you something really interesting. I'm sorry, let me tell you something interesting. So, this is a very fascinating thing, and again, you might have some interesting research problem. Maybe this problem is not exactly the problem, but, so X, let's say X is a Riemann surface, and Rembert tells us that this Riemann surface is in C3. Right? And then you ask a number of questions. Question 1, is it defined by holomorphic functions on C3? Everything I just said was local, but now I have functions on C3. Rangsatz and everything, all that good stuff is local. This is a global question. So is X, question mark, equal to the set of zeros, F1 to Fk, I don't know how many you need here, equals 0, for Fi holomorphic on C3? Isn't that a reasonable question? Zero sets of global functions. Manifold is only a zero set of local functions. This is zero sets of global functions. Yeah? And the answer is yes. And this answer is extremely deep. So it's a very interesting question. You have a local phenomenon, do you extend it to a global phenomenon? It exists locally, we know what it is. It exists locally as a zero set of two holomorphic functions, there's no problem. But globally, who the heck knows? So we want to know whether it's represented as the zero set of global functions. Then complex analysts work on this problem. And if the answer is yes, then I'm telling you, you should ask the next question. How many global functions do you need? It makes a difference. How many global functions do you need? Well, obviously you need more than at least 2, because if it's in C3, it's one-dimensional, so you need 2 functions to define it, at least. That's a question. How many global functions do you need? Are needed. It really makes a difference if you have at least 2 are needed, and if you have only 2, it's really good. It helps a lot of work, but you need at least 2. If you have exactly 2, so the codimension is 2, if in general you have a k-dimensional manifold, which is codimension n minus k, you certainly need n minus k functions. So, and I think it's a very interesting question. This question, how many functions do you need? So, mathematicians have given that a name. So, if X is k-dimensional, so in our case, k is 1, in Cn, we need at least n minus k functions, global functions. And if you're interested in complex analysis or mathematics in general, if they exist, such exist, then X has a name. X is called a complete intersection. And this is extremely useful and extremely beautiful. Here's how you should think. The blackboard is somehow C3. Let's say X and C3. Riemann surface. Here's X. And it's equal to F1 equals 0 and F2 equals 0. Those are the two functions that have to be 0. And here you have the level set of F1. It's codimension 1. It goes out to infinity, but I'm going to draw it here locally. This is F1 equals 0. And just for fun, maybe let me use another color here. And then you have the local set of zeros of F2. So this is F, and this part is F2 equals 0. Yeah. And the statement is these F1 equals 0 and F2 equals 0 are perfect, they're transversal. So F1 equals 0 and F2 equals 0 are transversal, are homomorphically transversal. Along X. And so that's the perfect situation when you have a complete intersection. And the theorem is you don't always have a complete intersection. It's very, very rare. So don't always have it. But you can get by with three functions. So you maybe can't get by with just two, but you can get by with three. Now, why the devil do you care about this? You don't care, you just do complex analysis, you're bored. Yeah. So my friend Andrew Somesi, who's a geometer, he's now doing applied mathematics, I will tell you why. Andrew Somesi was a geometer, now doing applied mathematics. Worked as a summer job when he was a professor, like we are here, for General Motors. General Motors makes automobiles. Its automobiles are not particularly good nowadays. The Japanese have really done much better. But they make several very good cars at General Motors. They used to make the cars in the United States. You've heard of General Motors, maybe. They make Chevrolet, for example. You've heard of that. Pontiac, Buick. And their best car is called a Cadillac. It's a very nice car, and they make SUVs now. In the summer, Andrew, an algebraic geometer, worked in General Motors' research lab on the problems concerning metals, metal in the sense of metal, that you make things out of. And they studied theoretical metals. So, no, these guys, you have to know that the private sector is interesting in these research labs. They're studying really interesting things. So they're studying the notion of a theoretical metal. So they have a lot of equations to solve. They have a lot of equations to solve. You can imagine, life is equations. So Andrew Somesi was presented with a huge number of equations to solve a huge number of problems with theoretical metals. And he said, well, you only need three. Well, it wasn't this context, but that's the kind of remark he was able to make, because he knows deep geometry. Actually, these are equations in projective space, and it's a matter of understanding something called Bezout theory. So he began working on algebraic geometric applications with computer science in applications in things like theoretical methods. Very, very non-trivial. Very, very interesting. Yes? Only because you can cut down the number of equations. You can imagine, cutting down the number of equations is a great thing to do. Right? So this fact, it's not a complete intersection but the fact that you only need 3 equations at most is already really a very nice fact for applications. Okay. By the way, some of the theoretical methods are now no longer theoretical, and they're being used. So this is really a serious matter of applied mathematics really doing something, and in this case, pure algebraic geometry. Okay, which gives these results. The equations are algebraic, as you might imagine. In nature, you don't have too many transcendental things. So it's a very, very interesting thing. This looks like some esoteric stuff I talked about, but it's really not, because you're really coming down to solving equations. Okay. Good. Now I have a few more minutes.
Can I just ask? I think I missed when you explained that, but what does it mean that f1 equals to and f2 equals to, that those sets are holomorphic transversal non-x?
Yeah. Well, in my picture you can see them cutting. Do you understand the notion of transversality in general?
No, that's I think.
Oh, okay. Well, it's a mathematical notion. Yeah, I guess it's only a mathematical notion. Okay. It means that they're not tangential. That you could imagine.
Mm-hmm.
And it means that if you have in each case you have the tangent space of this one and the tangent space of that one, right? It means that their tangent spaces intersect as I can't get the English word right. The intersection of the tangent spaces is as small as possible. Okay, and now there is the intersection. Yeah, you see, they intersect in something positive dimensional.
Mm-hmm.
They have to, because you have this curve here, and okay. But I hope you know a formula. Isn't there a formula? V, dimension of V. So we are. I don't know what is this formula. Somebody will tell me this Mickey Mouse formula. You have a vector subspace, so we have V1 and V2 vector subspaces of V. And now, let's see here, dimension of V1 plus dimension of V2. Well, what you would like equals dimension of V, right? You would love that, yeah? But I guess what you want is something like, that could be too big, right? Let's think about this for a minute. If you're in R2, and you're in R3 and you take 2 planes, and they should intersect in a line. 2 planes should intersect in a line, right? So dimension 2 plus 2 minus 1 is 3. There it is. So isn't that right? I mean, what could be terrible is that V1 equals V2. Right? If V1 equals V2, you don't get anything, right? But what you want to do is that they span the whole space, and so you will have exactly this thing. Right? And so what we're talking about is that's what Nico was asking about. We have the tangent space of the yellow thing, and that's V1, and the tangent space of the white thing is V2. And they intersect in the tangent space of the thing they're defining. And transversality, you should have the feeling, it cuts really transversally, and you should have the feeling of dynamics. It means if you move everything around here, it stays the same. Whereas if it's tangential, tangential moves to transversal quite often, but transversal never moves to tangential. Right? So it means generic intersection. Yeah, you should think like that. Okay. I think it's a good time to stop. I have many other things that I want to talk about, but going on, you're very tired, so thank you for your patience today. Keep asking the questions. I owe you some answers, but I enjoy answering your questions. And this is a course in topics and complex analysis. You will never see today's lecture, particularly the second half, in elementary complex analysis course, because elementary complex analysis was created in 1850. And this complex analysis was created 100 years later, and it's still growing and very important. So, see you.